there may be a planet somewhere among the nearest red stars where morning never arrives. On one hemisphere, the star hangs in the same part of the sky year after year. It does not rise from an eastern horizon or descend toward a western one. On the far side, the surface remains turned away beneath a night that may last for the entire age of the world. Between them lies a band of permanent twilight, a place where the star stays low, and every shadow points in nearly the same direction. This is the landscape suggested by tidal locking. It happens when a star's gravity gradually changes a planet's rotation until the time required to turn once matches the time required to complete one orbit. The moon keeps nearly the same face toward Earth for the same reason. Around a red dwarf, the habitable zone lies close to the star, where tidal forces can act strongly over long periods. Many rocky planets in such orbits are therefore expected to rotate synchronously, though eccentric orbits and other complications can produce different patterns. The result is not simply a world with a very long day. It is a world divided by geometry. Near the point facing the star, the light may remain high overhead. Farther away, it would rest at a fixed angle. Beyond the terminator, the star would never appear at all. Some places would never see noon. One place might know almost nothing else. These planets are not rare curiosities at the edge of astronomy. Red dwarfs are the most common kind of star in the Milky Way. They are smaller, cooler, and dimmer than the Sun, so a planet must orbit comparatively close to receive enough energy for liquid water to be possible at its surface. That closeness makes the planets easier to find in some ways. Their short years repeat often. Their transits block a larger fraction of their star's light. Their atmospheres, when atmospheres exist, can be studied during repeated passages across and behind the star. But closeness also creates the central difficulty of these systems. A red dwarf may be faint in visible light while remaining active in ultraviolet and X-ray wavelengths. Flares and stellar winds can reach planets moving through very tight orbits. Over time, that radiation may alter an atmosphere, erode it, or change the chemistry through which distant telescopes search for signs of a living world. And yet, tidal locking does not automatically make a planet lifeless. An atmosphere can carry heat from the day side toward the night side. Oceans, clouds, ice, and the movement of air may soften the contrast between permanent light and permanent dark. Climate models have shown that stable regions with temperatures suitable for liquid water may exist under a range of conditions. The answer depends on the atmosphere, the orbit, the star's history, and the planet itself. So, the question is not whether these worlds resemble Earth. Most will not. The deeper question is whether a planet must resemble Earth in order to become habitable. Tonight, the path leads inward toward the small stars that fill our galaxy, then outward across the close orbits of their planets. We will follow light that never moves across the sky, weather-driven by an unmoving sun, and climates stretched between an endless day and an endless night. Somewhere in that fixed landscape, the boundary between the two may be doing far more than dividing light from dark. To understand these planets, it helps to begin with the stars they circle. A red dwarf is not a weakened version of the Sun. It is a different kind of star, built from less material and governed by a slower internal balance. Most contain between roughly 1/10 and 1/2 the mass of the Sun. Their surfaces are cooler, their light is redder, and their total energy output can be only a small fraction of what pours from our own star. Yet they are not rare. Red dwarfs are believed to make up most of the stars in the Milky Way. Many are too faint to see without a telescope, even when they are close to Earth. The night sky is therefore a misleading census. The stars visible to your eyes are usually the brighter members of the galaxy, while the far more numerous red dwarfs remain hidden between them. A small star does not need to burn its fuel as quickly as a larger one. Deep inside, hydrogen nuclei are still being pressed together into helium, releasing the energy that supports the star against gravity. But the pressure and temperature in a red dwarf's core are lower than they are in the Sun. The reaction proceeds more slowly. In many low-mass red dwarfs, material can circulate through much of the entire star. Hot gas rises, cooler gas sinks, and hydrogen from the outer layers can gradually be carried inward toward the regions where fusion occurs. The Sun cannot use its fuel in quite the same way. Its internal layers restrict how freely material can mix, leaving much of its hydrogen beyond the reach of the core. A red dwarf may eventually consume a far greater share of its available fuel. This gives the smallest stars lifetimes that are difficult to place beside ordinary human ideas of duration. The Sun is expected to remain in its present stage for about 10 billion years in total. A low-mass red dwarf may shine for hundreds of billions of years, and the smallest could endure for trillions. No red dwarf has yet reached the end of such a life. The universe itself is only about 13.8 billion years old, so every true red dwarf that has ever formed is still shining. Astronomers can model their distant futures, but there are no ancient stellar remains available to confirm every stage through direct observation. These stars belong to a story whose ending lies beyond the present age of the cosmos. Their patience, however, can hide a more restless beginning. Young red dwarfs may rotate rapidly. Their magnetic fields can become tightly wound, storing energy that is later released in powerful flares. A star that looks dim and modest in visible light can suddenly brighten at ultraviolet or X-ray wavelengths. For a nearby planet, these outbursts may deliver intense radiation to the upper atmosphere. The danger is not determined by a single flare. A planet's fate depends on the star's behavior across millions or billions of years. Frequent eruptions can heat the upper atmosphere and help gas escape into space. Charged particles carried by the stellar wind may add to that loss. Ultraviolet radiation can break molecules apart and drive new chemical reactions, changing the atmosphere, even when it does not remove it entirely. A magnetic field may offer some protection, though not in every circumstance, and not as a perfect shield. A thick atmosphere may absorb radiation and redistribute energy. Volcanic activity may replace gases lost over time. Oceans and surface minerals may store carbon or release it. The outcome emerges from many processes working together. This is why the word habitable must be used carefully. Around the Sun, the traditional habitable zone describes the range of distances where a rocky planet might support liquid water at its surface, assuming suitable atmospheric conditions. Around a red dwarf, that zone lies much closer to the star because the star produces less energy. A planet may complete an orbit in only a few days or weeks. Its year could pass before a month has ended on Earth. At such a distance, the star's gravity raises tides not only in oceans, but in the solid body of the planet itself. These tidal distortions create friction inside the world. Rotation gradually loses energy. Over time, the spin can settle into a repeating relationship with the orbit. The simplest result is synchronous rotation. One rotation takes exactly as long as one orbit. The same hemisphere remains directed toward the star, but nature allows other arrangements. If the orbit is not perfectly circular, a planet may be captured into a different resonance, rotating several times during a fixed number of orbits. Mercury offers an example within our own solar system. It turns 3 times for every 2 journeys around the Sun. A red dwarf planet with the right orbital history might also avoid showing one face forever. Neighboring planets can disturb each other. Eccentricity can change. Tidal heating can continue within the interior. The spin state of a distant world may therefore contain evidences of its formation, its companions, and the long exchange of energy between motion and gravity. Even a synchronously rotating planet is not completely motionless beneath its sky. Its orbit carries it around the star. Its atmosphere moves, clouds gather and dissolve, waves cross an ocean, if an ocean is present. Weather systems may travel from the bright hemisphere into the dark one. The ground can warm and cool beneath changing cloud cover, even though the star itself never rises or sets. On the day side, the light of a red dwarf would not necessarily appear deeply red to human eyes. The star would look warmer in color than the sun, but the atmosphere would scatter and filter its light. The surface colors would depend on the air, the clouds, the soil, and the sensitivity of the observer. Plants, if anything resembling plants evolved there, would receive a spectrum different from the one that shaped life on Earth. Red and infrared wavelengths would be more abundant. Higher energy light might arrive irregularly during flares. Any photosynthetic system would have developed within that pattern from the beginning. Nothing there would be adapting from an earthly noon. The planet would have its own definition of daylight. For generations, people on Earth understood the sky through repeated movement. Sunrise marked direction. Noon divided the day. Sunset returned familiar stars. Seasons shifted the path of light across the horizon. These cycles became part of calendars, navigation, agriculture, and memory. On a locked planet, time could not be read in the same way. There would be no moving shadow to measure the hours. The star would not trace an arc. A traveler heading toward the dayside would see it climb higher, not because time had passed, but because distance had changed. A traveler moving into the night side would watch it sink and finally disappear. Location would replace the daily clock, and somewhere between the fixed star and the starless hemisphere, the atmosphere would be carrying energy across the world, deciding whether the night freezes, whether the day overheats, and whether the narrow region between them can remain stable for more than a passing moment. The first climate question on a locked planet is not how hot the dayside becomes. It is whether the atmosphere can move that heat before one hemisphere grows too warm and the other loses so much energy that the air itself begins to freeze. Sunlight arrives at one fixed region. The ground there absorbs part of it and warms the air above. That heated air expands, becomes less dense, and rises. Higher in the atmosphere, it begins to spread away from the point beneath the star. Some of it travels toward the night side. There, far from direct light, the air cools and descends. Near the surface, winds can return toward the illuminated hemisphere, completing a circulation pattern that reaches across much of the planet. On a slowly rotating world, this broad dayside to nightside flow may dominate the atmosphere. The planet behaves less like Earth, with many moving weather systems shaped by a rapid daily rotation, and more like one immense thermal engine. Heat enters in one region. The atmosphere lifts it, carries it around the globe, and releases it where the star never appears. The strength of this engine depends greatly on the amount of air present. A thin atmosphere stores little heat and transports it poorly. Surface temperatures may then follow the light very closely, rising sharply near the substellar point and falling across the dark hemisphere. A denser atmosphere can absorb more energy and move more of it. Winds, pressure waves, and large-scale circulation reduce the contrast between day and night. A planet with enough air may keep parts of its night side far warmer than a bare rock at the same distance from the star. The composition matters as much as the pressure. Carbon dioxide, water vapor, methane, and other greenhouse gases absorb outgoing infrared radiation. They can slow the loss of heat to space and give atmospheric circulation more time to redistribute energy. Nitrogen does not contribute much greenhouse warming by itself, but it can add pressure, broaden the absorption of other gases, and increase the atmosphere's capacity to carry heat. There is no single atmospheric recipe for habitability. A world with a dense carbon dioxide atmosphere might remain warm, but develops surface conditions unlike anything comfortable for life as we know it. A thinner atmosphere rich in water vapor could support clouds and rainfall, while remaining vulnerable to escape during the star's active youth. A planet that began with large amounts of gas might lose much of it and still retain enough circulation. Each atmosphere is also part of a longer history. May have been delivered during formation, released from the interior through volcanism, altered by oceans, absorbed into rocks, or gradually stripped from the upper layers. What a telescope observes today may be the remnant of several billion years of exchange between the surface, the interior, the star, and space. On the illuminated hemisphere, one feature may change the climate more than the permanent sunlight alone. Clouds, warm air rising near the substellar region, can carry water vapor upward. As the air expands and cools, that vapor may condense into a broad shield of clouds above the brightest part of the planet. Clouds reflect part of the incoming starlight before it reaches the surface. A thick, persistent cloud deck could therefore prevent the center of the day side from becoming as hot as a cloudless calculation might suggest. This creates an unusual form of climate stability. More sunlight warms the surface. Stronger heating produces more rising air. Rising air forms more clouds. The clouds reflect more light, limiting further warming. The effect would depend on the planet's rotation, atmospheric depth, water supply, and cloud physics. Clouds are among the hardest parts of any climate to model, including Earth's. Yet repeated simulations have shown that a synchronously rotating world can sometimes develop this bright dayside canopy, widening the range of stellar energy under which surface water might remain possible. Seen from far away, such a planet might change brightness as different portions of its fixed cloud pattern face the observer. The star would remain over the same place on the surface, but the planet's motion around the star would reveal changing angles of its atmosphere. Future telescopes may search for those variations. They may measure heat emitted from the day side and night side at different stages of the orbit. A small temperature difference could indicate efficient atmospheric transport. A large difference might suggest thin air, weak circulation, or perhaps no substantial atmosphere at all. A planet does not need to be photographed as a detailed sphere for its climate to leave a trace. Its warmth can become a rhythm in the light. The night side presents a different challenge. If it grows cold enough, water vapor can freeze onto the surface. Over long periods, glaciers may accumulate beneath the permanent night, gradually drawing water away from the day side. This is sometimes called cold trapping. On a planet with limited water, the dark hemisphere might become a deep reservoir of ice. Snow, carried by winds, could settle there and rarely melt. Glaciers could thicken, flow under their own weight, and slowly reshape the surface. But permanent ice does not always mean permanent loss. Ice can move. Geothermal heat can melt it from below. Atmospheric circulation can carry moisture back toward the light. If glaciers extend into warmer regions near the terminator, melting and evaporation may return water to the active climate. The planet's interior remains part of the system, even where no sunlight falls. Radioactive elements release heat as they decay. Residual energy from formation escapes gradually through rock. Tidal flexing may add more, especially if the orbit is slightly eccentric, or neighboring planets continue to disturb it. In some regions, water beneath the ice might remain liquid. The night side could contain buried lakes, slow glaciers, volcanic provinces, or oceans sealed under frozen surfaces. None of these possibilities can be assumed for a particular world, but they show why permanent darkness is not the same as complete geological stillness. The air itself may also be vulnerable to the cold. Carbon dioxide can condense under sufficiently low temperatures and pressures. nitrogen can freeze in more extreme conditions. If too much of the atmosphere settles onto the nightside surface, pressure falls across the planet. Circulation weakens, allowing further cooling and additional collapse. This feedback can remove much of an atmosphere. Yet, models suggest that many locked planets can avoid it. Enough atmospheric pressure, greenhouse warming, or heat transport can keep nightside temperatures above the condensation points of major gases. Ocean currents may provide further support. An ocean does not wait passively beneath the sky. Water absorbs heat near the dayside and can carry it through currents toward colder regions. Winds push the surface. Differences in temperature and salinity drive deeper motion. Continents redirect the flow, creating local climates that depend on geography as well as starlight. A planet covered almost entirely by ocean might distribute energy efficiently across great distances. A world divided by large continents could create enclosed seas, dry interiors, and strong regional contrasts. If the night side held a global ice sheet, the location of coastlines near the twilight zone might determine where meltwater gathered and whether open ocean remained. From orbit, all of these landscapes would fit inside a point of light. There could be rain beneath the fixed star, snowfall beyond the last dim arc of twilight, and ice moving through a night that has never known sunrise. There could be ocean currents crossing under the terminator, carrying warmth into places as the star cannot reach directly. The terminator itself is often imagined as the natural refuge of such a world. There, the star would remain close to the horizon. Temperatures might fall between the heat of the dayside and the cold of the night. A ring of moderate conditions could circle the planet, neither fully illuminated nor fully dark. But this picture is too simple to apply everywhere. A strong atmosphere might make much of the dayside and even part of the nightside temperate, removing the need for a narrow habitable band. A thin atmosphere could produce severe temperature changes across a short distance. Mountains might block winds. Oceans might carry warmth far beyond the expected boundary. Clouds could cool one region while greenhouse gases warm another. The most favorable place might lie near the terminator. It might also lie beneath the substellar cloud deck, along a dayside coast, or under ice on the dark hemisphere. Habitability is not a line drawn neatly between day and night. It is a moving result produced by air, water, rock, ice, clouds, gravity, and time, all working beneath a star that never changes its place in the sky. A red dwarf can look almost motionless from far away, but its influence reaches a planet through more than visible light. The star sends out ultraviolet radiation, X-rays, charged particles, and magnetic disturbances. Some arrive as a steady background, others come in sudden bursts. For a planet orbiting close enough to remain warm, there is little distance in which these emissions can spread and weaken. This changes the meaning of sunlight. On Earth, visible light warms the surface, while the upper atmosphere absorbs much of the most damaging radiation. Ozone blocks a large portion of the sun's ultraviolet light. The magnetic field redirects many charged particles. The atmosphere itself acts as a deep chemical shield, turning a hostile stream of energy into something life can live beneath. A planet around a red dwarf may or may not possess the same protections. Its first challenge may begin long before the star settles into the calmer part of its life. Young red dwarfs can remain brighter and more active than their later appearance would suggest. During this early phase, a planet now located in the habitable zone may once have received far more energy. Surface water could have evaporated into the atmosphere. High above the planet, ultraviolet light could split water molecules apart. The lighter hydrogen might escape into space, while oxygen remained behind or reacted with the surface. A world can therefore enter its mature orbit, carrying the memory of an earlier climate. It might still have oceans. It might have lost many of them. It might possess an oxygen-rich atmosphere created without biology, simply because water was broken apart and hydrogen escaped. This is one reason the search for life cannot depend on finding a single gas. Oxygen can be produced by living systems, but under some conditions it can also accumulate through non-living chemistry. The atmosphere must be read as a whole. Astronomers look for combination of gases that make sense together, along with the temperature, pressure, clouds, surface conditions, and behavior of the star. Methane beside oxygen may be more suggestive than oxygen alone, because the two gases tend to react and remove each other unless some process continues to replace them. Even then, geology and photochemistry must be considered before biology. A red dwarf makes this interpretation harder because its light drives chemistry in a different way from the sun. The balance between visible, ultraviolet, and infrared radiation changes how molecules break apart and reform. A planet with the same gases as Earth could develop a different upper atmosphere under a different stellar spectrum. Ozone might build efficiently in one case and remain limited in another. Methane could persist longer. Haze could form. Clouds could alter the amount of light reaching the ground. The chemistry of the sky is tied to the color and activity of the star. During a flare, ultraviolet and X-ray output can rise sharply. Energetic particles may follow. In the upper atmosphere, these events can ionize gases, create new compounds, and damage protective molecules. A single flare may cause only temporary change. Repeated flares over long periods can push the atmosphere toward a different chemical state. But activity is not always a simple sentence of loss. Radiation can destroy complex molecules, yet it can also provide energy for chemistry. On the early Earth, ultraviolet light may have helped drive some of the reactions that preceded life, especially where water, minerals, and simple carbon-bearing compounds met. On another planet, intermittent bursts from a small star might create cycles of reaction and recovery. Too much energy can strip and sterilize. Too little can leave chemistry without enough drive. Between those outcomes lies a broad and uncertain range. The planet's gravity matters. A larger, rocky world can hold gas more tightly than a smaller one. Temperature matters because warm molecules move faster and escape more easily. Atmospheric composition matters because some gases cool the upper atmosphere while others heat it. A magnetic field may reduce some forms of particle-driven loss, though its effect depends on the strength of the field, the shape of the stellar wind, and the structure of the upper atmosphere. Even the absence of a strong global magnetic field does not guarantee that the atmosphere disappears. Venus has no Earth-like global magnetic field, yet it retains a dense atmosphere. Mars once had a thicker atmosphere and lost much of it, but its lower gravity, smaller size, and long history also shaped that outcome. These worlds remind us that no single shield determines survival. For a locked planet, the interior may influence that shield. Rotation helps organize a planet's magnetic dynamo, but synchronous rotation does not always mean extremely slow rotation. A planet orbiting a red dwarf every 10 days may rotate once every 10 days, which is slower than Earth, but far faster than the Moon's month-long cycle around us. Convection in a liquid metallic core, internal heat, composition, and the history of the planet all contribute. Some locked worlds may generate magnetic fields, others may not. And even when a field exists, the star may press its protective region close to the atmosphere. The stellar wind near a red dwarf can be dense and magnetically complex. The planet's magnetic boundary may expand and contract as flares and eruptions pass. Above the clouds, the planet may be living inside weather created by the star. This weather has no sound at the surface. There is no thunder rolling through the air when charged particles sweep past the planet. The disturbance placed is in magnetic fields, ionized gas, and the thin upper edge of the atmosphere. Yet its effects can descend into chemistry. Nitrogen and oxygen molecules can be broken apart. New compounds can form. Atmospheric heating can increase escape. Auroras may spread far beyond the polar regions if the magnetic geometry allows them. On the night side, curtains of color could appear beneath a sky where the star itself is never visible. That image is only a possibility, not a prediction for every world. Color, brightness, and location of auroras would depend on the gases present and the way charged particles enter the atmosphere. A planet without oxygen would not produce Earth's familiar green glow in the same way. A hydrogen-rich atmosphere might shine differently. A dense carbon dioxide sky would have its own emissions. The night could reveal the star without showing its disk. Energy arriving from the dayside direction might travel along magnetic paths and light the upper atmosphere above the dark hemisphere. For an observer below, the star's presence would be written overhead in shifting color, rather than sunrise. Long before telescopes could measure atmospheres around distant planets, people on Earth watched auroras and tried to understand why the sky moved while the stars remained fixed behind it. Some treated them as signs. Others recorded their shapes, colors, and seasons. Later, science connected them to the sun, the magnetic field, and charged particles crossing space. That same connection now reaches beyond the solar system. When astronomers study a red dwarf, they are not only measuring the star, they are measuring the environment of every close orbiting planet around it. The timing and energy of flares, the strength of X-ray emission, the rotation rate, and the age of the star all help define what its planets have endured. Age is especially important. Young red dwarfs often rotate quickly and remain highly active. As they lose angular momentum over time, many spin more slowly, and their activity can decline. But the path is not identical for every star, and some remain active for billions of years. A planet may therefore pass through different eras. Its early sky might be battered by frequent flares. Later, the star may calm. If the atmosphere survives the first era, the second may offer a long period of stability. Because red dwarfs burn for such immense spans of time, a planet that remains habitable could have far more time than Earth has had so far. The difficulty is crossing the beginning. Some worlds may start with deep oceans, thick atmospheres, or large stores of water locked in minerals. Volcanism may replace gases lost to space. Impacts may deliver additional material. Chemical reactions with the crust may absorb excess oxygen or carbon dioxide. A planet that looks dry today may once have been wet, while a planet with water today may have survived losses that would have emptied a smaller world. The visible surface is only the final page of a much longer history. This is why nearby red dwarf planets are so valuable. They allow astronomers to compare worlds exposed to different stars, different flare rates, and different ages. One planet may show signs of a thick atmosphere. Another may appear bare. A third may remain uncertain because clouds hide its lower layers. Across many systems, patterns may emerge. Perhaps atmospheres survive more often around older, quieter red dwarfs. Perhaps water-rich planets retain enough to remain stable. Perhaps thick carbon dioxide atmospheres are common, while Earth-like mixtures are rare. Perhaps some worlds lose almost everything. The answer will not come from one planet alone. It will come from a population. For now, every atmosphere around a small star is a difficult signal. Starlight must pass through a thin ring of gas during transit, or the planet's own faint heat must be separated from the glare of the star. Stellar spots and flares can imitate atmospheric features. Clouds can hide molecules. The same data may support several models. The work advances by narrowing uncertainty, rather than removing it all at once. A spectrum reveals an absorption feature. Another observation tests whether it repeats. A model asks what combination of temperature and chemistry could produce it. The star is measured again. Slowly, a world begins to take shape. Not as a photograph, but as a set of constraints. Its atmosphere may be dense or thin. Its night side may be warm or frozen. Its water may be abundant, buried, or gone. Its star may have spent billions of years wearing away the sky, or may have left enough of it intact for winds and clouds to keep moving. And beneath that atmosphere, the planet continues to turn once for every orbit, carrying the same face toward the source of both its warmth and its greatest uncertainty. The nearest examples of these worlds do not form a single pattern. They appear in compact systems around solitary stars and beside stellar companions. Some are probably bare, some may retain atmospheres, some travel through separate levels of starlight, while receiving bursts of radiation that complicate every simple definition of habitability. Together, they offer a set of natural experiments. The closest known planet beyond the solar system orbits Proxima Centauri, the small red dwarf, to Alpha Centauri. Proxima Centauri b completes a year in a little over 11 Earth days. Its orbit places it within the region where surface water could be possible under suitable atmospheric conditions. From the planet, Proxima would remain much larger in the sky than the Sun appears from Earth. Yet because the star is cooler and dimmer, the total energy reaching the world may fall within a temperate range. The orbit is close enough that tidal effects are expected to be important. The planet may keep one side toward the star, or it may have settled into another repeating spin pattern if its orbit and internal history allow it. Very little is known directly about the surface. The planet was discovered through the motion it produces. In its star, its gravity pulls Proxima slightly toward and away from Earth. As the two orbit their shared center of mass, that motion changes the wavelengths of the star's light by a tiny amount. From this rhythm, astronomers can measure the orbital period and estimate a minimum planetary mass. They cannot yet see continents, oceans, or clouds. Even the atmosphere remains uncertain. Proxima is an active star, and it produces powerful flare enough to receive far more high-energy radiation than Earth receives from the Sun. This has led to models in which the atmosphere is eroded over time. Other models begin with a thicker atmosphere, a larger water supply, or a protective pattern of circulation, and find that some gas could survive. Neither result is a direct observation of the planet as it exists now. Proxima b remains a question written in gravity. Farther away, a small star called TRAPPIST-1 carries 7 known planets through a space smaller than the orbit of Mercury. Every one of them is close to Earth in size. Their years range from only a few Earth days to less than 3 weeks. The planets are arranged in a chain of orbital resonances. Their motions are linked. As one planet circles the star, its repeated gravitational encounters with the others cause small changes in transit timing. These delays and advances allow astronomers to estimate their masses, even though the planets are too distant to weigh directly. The system resembles a mechanical clock whose hands pull faintly on one another. Several of its worlds receive amounts of starlight that make them important targets in the search for temperate climates. Yet the planets cannot be treated as copies of Earth, placed at convenient distances. TRAPPIST-1 is cooler than Proxima and only a little larger than Jupiter, though it contains far more mass. Its light is concentrated toward red and infrared wavelengths. The planets orbit so close that synchronous rotation is expected for most, or all of them. Their climates may differ sharply, even between neighboring orbits. An inner planet may have lost much of its atmosphere through heat and radiation. A world slightly farther out might retain dense gas or water. Another could be frozen at the surface while holding liquid beneath ice. Small differences in mass, composition, and formation history may have become large differences over billions of years. The system is valuable because many of those differences can be studied around the same star. The planets formed from related material. They experience the same broad stellar history. Their present conditions, therefore, offer a way to separate the effects of distance, size, atmosphere, and internal evolution. When one of the planets passes in front of TRAPPIST-1, it blocks a small portion of the star's light. If the planet has an atmosphere, some starlight passes through the thin edge of that air before reaching a telescope. Molecules absorb particular wavelengths, leaving patterns in the measured spectrum. The signal is delicate. The atmosphere forms only a narrow ring around the planet. Stellar spots can change the spectrum. Flares can interrupt observations. Clouds or hazes may flatten molecular features. Several transits may need to be combined before a pattern becomes clear. A missing feature does not always mean a missing atmosphere. It may mean the atmosphere is too compact, too cloudy, or made of molecules that are difficult to detect at the available wavelengths. It may also mean the star has changed during the observation. Each measurement has to be compared with models of both planet and star. Another important system surrounds the red dwarf LHS 1140. One of its planets, LHS 1140b, is larger and more massive than Earth and travels through a temperate orbit lasting about 25 days. Its higher gravity may help it retain an atmosphere. Its density suggests a world dominated by rock and perhaps a significant amount of water, though the internal structure is not known with certainty. Because the planet passes in front of its star, astronomers can measure both its radius and mass. Those values provide an average density, which narrows the range of possible interiors. But density alone cannot reveal a unique planet. A large rocky core beneath a thick atmosphere can resemble a world containing a deep layer of water. Different mixtures of iron, silicate rock, ice, and gas can produce similar total measurements. The same distant point may support several physical stories. TY 700 offers another arrangement. This red dwarf hosts multiple known planets, including small worlds that receive moderate amounts of stellar energy. Their discovery shows how space telescopes can find planets by monitoring thousands of stars for repeated dips in brightness. Each dip records a transit. The depth suggests the planet's size relative to the star. The interval between dips gives the orbital period. Changes in duration can reveal the geometry of the orbit. Later observations refine the planetary radius and test whether the signal truly repeats. Red dwarfs are useful for this method because they are small. An Earth-sized planet crossing the Sun would block only a tiny fraction of its light. The same planet crossing a much smaller star covers a larger part of the stellar disk, producing a deeper and more measurable signal. The close habitable zone also means transits occur frequently. Earth passes in front of the Sun from a distant observer's perspective only once each year. A temperate planet around a red dwarf may transit every few weeks. Many events can be observed within a telescope's working life. This advantage comes with a complication. A planet can transit only when its orbit is aligned closely with our line of sight. Most planetary systems are tilted at angles that prevent transits from being seen from Earth. The absence of a transit does not mean the absence of a planet. Radial velocity searches can find some non-transiting worlds, but they work best when the star's own activity is understood. Spots rotating across a stellar surface can create apparent motions that resemble planetary signals. Magnetic cycles can shift spectral lines. Flares can add noise. The same active star that shapes its planets also makes them harder to detect. Direct imaging offers a different possibility. Instead of waiting for a transit or measuring stellar motion, a future telescope may block the light of a nearby red dwarf and search for the much fainter light reflected or emitted by its planets. This requires separating two points that appear extremely close together in the sky. It also requires suppressing starlight by an enormous factor without erasing the planet beside it. A coronagraph can perform part of this work inside a telescope by controlling the diffraction of light. A separate spacecraft called a starshade could, in principle, fly far ahead of a telescope and cast a carefully shaped shadow over its optics. Inside that shadow, the star would fade enough for nearby planets to appear. A directly measured spectrum could reveal gases and clouds without requiring the planet to transit. Repeated observations might show seasonal changes, rotating surface patterns, or differences between the illuminated and dark hemispheres. For a locked planet, brightness may vary in a distinctive way as it moves through its orbit. At one point, an observer sees mostly the day side. Half an orbit later, the night side faces Earth. The changing infrared signal forms a phase curve, a record of how heat is distributed around the globe. A world with no atmosphere may show a strong contrast. Its bare day side heats rapidly, while the night side remains cold. A world with thick air may produce a smoother curve, because winds carry energy into the dark. Clouds can shift the brightest region away from the point directly beneath the star. Ocean currents may add further changes. From these faint variations, astronomers can begin to reconstruct the circulation of a planet that is never more than a speck. None of these measurements will reveal habitability in one step. A planet may occupy the right orbit and lack water. It may contain water beneath pressure too great for familiar life. It may hold a stable atmosphere with no biology. It may have surface conditions that change with flares, volcanic cycles, or the slow loss of gas. The task is to build a complete environment from separate clues. Mass provides gravity, radius limits the interior, the orbit sets the average stellar energy. The star's spectrum drives atmospheric chemistry, transits probe gases near the planetary edge. Infrared emission traces temperature. Phase curves reveal circulation. Together, these fragments replace the simple image of a world in permanent twilight with something more detailed. There are many kinds of locked planets. Some may be dry stone beneath a fixed red sun. Some may be wrapped in deep air. Some may carry ice across the night side and open water beneath clouds on the day. Others may have lost the conditions required for surface water before their stars reached maturity. The galaxy does not appear to have built one answer and repeated it. It has built a range of worlds, each turning through a short orbit, each carrying its own history beneath a star that stays in one place above the ground. Life on a world without sunrise would not experience time as life on Earth does. Here, nearly every surface ecosystem is shaped by cycles of light and dark. Plants open and close, animals sleep, migrate, hunt, and reproduce according to patterns connected to the turning planet. Even organisms sheltered in caves or beneath the sea often carry inherited biological clocks whose origins lie in the daily passage of sunlight. On a synchronously rotating planet, the star would not provide that rhythm. The day side would remain illuminated, the night side would remain dark. A region near the terminator might know a dim, unchanging glow, but not dawn or evening. Any life that developed there would begin with this arrangement. It would not feel the absence of sunrise, because sunrise would never have been part of its world. Its rhythms would have to come from somewhere else. Tides might provide one clock. If the planet traveled in a slightly eccentric orbit, the strength of tidal forces could vary in a repeating pattern. A neighboring moon, if one existed in a stable orbit, might create additional cycles. Atmospheric waves could pass regularly around the planet. Volcanic activity, ocean circulation, or periodic stellar flares might divide time into intervals that living systems could detect. Seasons are also possible. Tidal locking fixes the relationship between rotation and orbit, but it does not necessarily remove axial tilt or orbital eccentricity. A tilted world could experience changes in the angle of illumination as it traveled around its star. The star would remain in roughly the same region of the sky, yet its height might shift. The boundary between day and night could move north and south. Temperatures and rainfall might change across the year. The seasons would not resemble those of Earth, but they could still organize biological activity. Along the day side, the first requirement for familiar surface life would be energy. Red dwarfs produce less visible light than the sun, and a larger share of their radiation in red and near-infrared wavelengths. Photosynthesis like that used by plants on Earth depends strongly on visible light, especially in blue and red portions of the spectrum. Around a red dwarf, the available balance would be different. This does not mean photosynthesis would be impossible. Pigments evolve in response to the light that reaches an environment. On Earth, chlorophyll absorbs certain wavelengths efficiently, while reflecting much of the green light that gives leaves their familiar color. Other organisms use different pigments. Some bacteria absorb light beyond the range used by plants, and many photosynthetic communities combine several light-harvesting molecules. On another planet, evolution could favor pigments tuned to the spectrum of the local star. A surface organism might appear dark because it absorbed nearly every useful wavelength. It might reflect colors that seem unfamiliar beside Earth vegetation. In shaded regions or beneath water, life might use narrow portions of red and infrared light that penetrate the surrounding material. There are physical limits. Longer wavelength photons carry less energy than shorter wavelength ones. Chemical reactions that require a certain amount of energy may need several lower energy photons instead of one more energetic photon. A photosynthetic system beneath a red dwarf might therefore use a more complex sequence of steps. This remains a field of models and experiments rather than observation. No one has seen a living surface beyond Earth. Scientists can test what known pigments absorb, calculate the energy available under different stars, and consider how alternative systems might work. The possibilities are constrained by physics, but not reduced to a single color of leaf. The atmosphere would alter the light before it reached the ground. Water vapor, carbon dioxide, clouds, dust, and haze would absorb or scatter different wavelengths. A thick cloud deck near the substellar region might reduce the total light, while providing stable temperatures beneath it. Clearer regions farther from the center of the day side might receive weaker illuminations but more reliable access to the stellar spectrum. Life could follow those patterns. Some organisms might remain beneath protective water, where the liquid absorbs damaging radiation. Others might live under soil, ice, or mineral layers thin enough to admit useful light. Surface activity could increase during calmer stellar periods and retreat during episodes of intense radiation. Flares would complicate the energy supply. To a human observer, a strong flare might appear as a brief brightening of the star. To a planet, it could deliver a sudden pulse of ultraviolet light and energetic particle. The atmosphere might absorb much of that energy, but upper layers would change rapidly. Any surface life would need to survive the conditions that reached the ground. Protection could take many forms. Organisms might repair molecular damage efficiently. They might produce screening pigments. They could remain dormant during periods of high activity, or live beneath water, rock, salt, or ice. Life on Earth already occupies environments where radiation, temperature, acidity, pressure, or dryness would be lethal to most organisms. These examples do not prove that life exists on red dwarf planets. They show only that biology can persist through a wider range of conditions than surface animals and plants might suggest. The origin of life presents a different question. Habitability describes whether an environment could support living processes. It does not explain whether those processes begin easily, rarely, or only under a narrow set of circumstances. A planet might remain warm and wet for billions of years without producing life. Another might develop simple organisms quickly. At present, Earth is the only example available. And one example cannot reveal how common the transition from chemistry to biology may be. Red dwarf systems could offer long periods of time for that transition. Once a small star settles after its active youth, it may shine steadily for far longer than the Sun. If a planet retains water, air, and chemical stability, its habitable era could continue for tens or hundreds of billions of years, perhaps longer. Time alone does not guarantee life, but it changes the scale of opportunity. On Earth, life appeared relatively early in the planet's history, though the exact timing and pathway remain uncertain. Multicellular organisms arrived much later. Technological civilization appeared only during a minute fraction of the time life has existed. Around a red dwarf, the biological clock might have far more room to run. There could also be interruptions, flares, atmospheric loss, climate shifts, volcanic episodes, and changes in ocean chemistry might repeatedly alter the surface. A long-lived star provides duration, but not necessarily uninterrupted calm. If life persisted, the geography of a locked planet could create distinct ecological provinces. Near the center of the dayside, temperatures might be moderated by reflective clouds. Rain could fall beneath rising air. Rivers might flow outward toward cooler regions. If continents occupied this area, erosion and weathering could move minerals into lakes and seas farther from the fixed star. Illumination would arrive at a lower angle. Landscapes might stretch through long shadows. Temperatures could become milder or colder depending on winds and elevation. Vegetation-like organisms, if present, might orient broad surfaces toward the unmoving light. Near the terminator, the star would rest close to the horizon. Mountains could cast shadows, extending for great distances. One side of a ridge might receive permanent illumination, while the other remained frozen. Valleys could trap cold air. Coastal regions might collect meltwater from glaciers advancing out of the night. Beyond the last direct light, ecosystems would need other sources of energy. On Earth, deep-sea communities survive without sunlight around hydrothermal vents. Microorganisms use chemical energy released when water reacts with hot rock and dissolved minerals. Similar processes could occur beneath an alien ocean or within a planet's crust. A dark hemisphere may therefore contain habitable regions that are almost independent of the star's visible light. Tidal heating could support geological activity. Radioactive decay could warm underground water. Chemical gradients could persist where rock, gas, and liquid met. An atmosphere carrying material from the dayside might deliver additional nutrients into the night. If the ocean connected both hemispheres, life could circulate between them. Currents might carry microscopic organisms beneath ice through twilight waters and into brighter seas. Nutrients released near the seafloor could rise toward the surface. Organic material created on the dayside might sink and drift into dark regions, feeding ecosystems that never encounter the star. The permanent night would not be empty merely because it was dark. It might be the receiving half of a planetary metabolism. Even the atmosphere could connect distant ecosystems. Winds could carry spores, cells, dust, vapor, and chemical compounds across the terminator. Material lifted beneath the fixed star might settle on ice thousands of miles away. Seasonal shifts or atmospheric waves could return part of it. The whole planet would function as one linked environment, even where its surface appeared divided into separate worlds. A biosphere can also alter a planet. Life on Earth changed the atmosphere through photosynthesis, transformed minerals, influenced cloud formation, and became part of the cycling of carbon, nitrogen, sulfur, and water. If life became widespread on a red dwarf planet, it might also leave changes large enough to be measured from afar. Astronomers would search for gases that appear out of chemical balance, but no gas would provide certainty by itself. Oxygen, methane, nitrous oxide, and other possible biosignatures can have non-biological sources. Stellar ultraviolet radiation may create or destroy them at rates unlike those on Earth. A reliable interpretation would require knowledge of the star, the atmosphere, the surface, and the planet's climate. Clouds could hide important features. Haze might create patterns that resemble biological activity. A dry planet could accumulate oxygen after losing water. Volcanism could release methane. Mineral reactions could remove gases that life produces. The search would therefore proceed through combinations. A planet with liquid water conditions, a stable atmosphere, several mutually reactive gases, and a stellar environment consistent with their persistence would become an interesting candidate. It would still not become a confirmed living world. Confirmation may require repeated observations with different instruments, the elimination of non-living explanations, and perhaps evidence of surface variation tied to seasons or planetary rotation. On a locked planet, that last measurement would be unusual. The same large-scale regions would face the observer at the same parts of every orbit. Reflected light might reveal a stable contrast between clouds, ocean, land, and ice. Changes over time could indicate weather, seasonal motion, volcanic activity, or biology. A distant telescope might never see a forest or an animal. It might see only a slight difference in color, a repeating gas pattern, or heat moving across the boundary between day and night. From such small clues, an inhabited world could begin to separate itself from. For now, these possibilities remain unconfirmed. No atmosphere around a temperate rocky red dwarf planet has yet provided accepted evidence of life. Many of the nearest worlds remain difficult even to characterize. Still, the question has changed. There was a time when a planet locked to its star was often imagined as a simple failure of climate, with one side scorched and the other frozen. Models now reveal a wider range. Air can circulate, oceans can transport heat, clouds can protect the dayside, ice can preserve water, chemistry can continue in places the star never reaches, and if life can begin within those conditions, it would not spend its existence waiting for morning. It would belong to the fixed light, the long horizon, and the connected climates of a world whose sun never crosses the sky. The first clear answer may not arrive as an image. It may arrive as a slight change in infrared brightness measured during the hours when a planet slips behind its star. At that moment, the telescope receives the star alone. Just before the disappearance, it receives the star and the planet together. Subtracting one measurement from the other can reveal the faint heat of the world. This is called a secondary eclipse. For a hot rocky planet, the effect is easier to detect because the day side glows strongly in infrared light. For a temperate world, the signal is smaller. The telescope must remain stable while the star flickers, rotates, and flares. The observation is not a photograph, but a temperature hidden inside a difference between two measurements. Yet that difference can tell us whether heat is escaping quickly from bare rock or being held and transported by an atmosphere. If the day side is much hotter than expected, the planet may have little air to move energy away. If the brightness is reduced or shifted through the orbit, winds or clouds may be carrying heat toward the night. Around TRAPPIST-1, the James Webb Space Telescope has begun making these measurements one planet at a time. The innermost worlds receive far more energy than the temperate members of the system. Observations of TRAPPIST-1b have favored a surface with little or no substantial atmosphere. Results for TRAPPIST-1c also argue against a thick carbon dioxide envelope, though a very thin atmosphere has been harder to exclude. Farther out, the measurements become more difficult. The cooler planets have weaker infrared glows, requiring more transits and eclipses. The star's spots and changing surface can leave patterns in the same wavelengths scientists are trying to assign to the planets. For TRAPPIST-1d and E, observations have narrowed the possibilities without revealing a complete atmosphere. Thick, hydrogen-rich envelopes have been ruled out, and some dense carbon dioxide scenarios have become less likely. But thinner atmospheres, clouds, and other compositions remain possible in the data. This is how the search advances, not by announcing what a world is, but by removing what it cannot be. A spectrum may show no strong carbon dioxide feature. That absence limits pressure, temperature, cloud height, or composition. A thermal measurement may show that the day side releases energy efficiently. A series of transits may reveal that a feature belongs to the star rather than the planet. Each result reduces the number of climates that can still fit. The star is the greatest source of light and a major source of confusion. When a planet crosses a red dwarf, it blocks a small region of the stellar disk. If that region is cooler because of a star spot, or hotter because of a bright magnetic area, the transit spectrum changes. The variation can resemble absorption by a planetary atmosphere. The planet may seem to contain water, methane, or another molecule, when the pattern has actually been written by the uneven surface behind it. Astronomers call this stellar contamination. To correct for it, they observe the star before, during, and after the transit. They measure its rotation, track spots across many wavelengths, compare repeated crossings, and build models of the stellar surface. A clean planetary spectrum may require a detailed portrait of the star first. Flares create another problem. A large eruption can interrupt a transit or alter the atmosphere during the observation. Smaller changes can be harder to notice. The star may appear nearly steady while its ultraviolet output or magnetic activity shifts in ways that matter to the planet's chemistry. For this reason, observations from different kinds of telescopes are combined. One instrument measures visible light and stellar rotation. Another records ultraviolet or X-ray activity. A spectrograph on the ground searches for planetary motion. Webb studies infrared emission and transmission. Together, the measurements create context around the faint atmospheric signal. The most useful answer may come from repetition. A single transit can contain noise. Repeated crossings can reveal which features return and whether a suspected molecule follows the planet's orbit or the star's rotation. A telescope may spend many hours collecting photons from a planet that never appears as more than a change in a graph. Researchers compare atmospheric models, each capable of explaining part of the data. New observations are chosen not merely to gather more light, but to separate those models from one another. One wavelength may distinguish carbon dioxide from cloud. Another may reveal water vapor. A phase curve may test heat transport. The planet becomes clearer through the design of questions. Large ground-based telescopes will add another kind of reach. The coming generation of observatories, with mirrors far wider than those used today, will collect more light and separate finer details in the sky. High-resolution spectrographs can divide starlight into many narrow wavelengths and search for the motion of molecules in a planet's atmosphere. The planet and star move at different speeds. Their spectral lines shift by different amounts. With enough precision, a faint planetary pattern can be separated from the much stronger stellar spectrum, rather like hearing a moving instrument inside a crowded room. Because its note slides in pitch, this method may be especially useful for nearby red dwarfs. Their planets orbit rapidly, Their systems are brighter than similar stars farther away, and their small size increases the relative strength of a transit. But every advantage returns to the same difficulty. The planets are close to active stars. The signals are larger, yet the environment is more complicated. Future space telescopes designed for direct imaging may eventually separate the light of nearby rocky planets from their stars. A coronagraph would suppress the central glare inside the telescope. For red dwarf systems, the habitable zone lies so close to the star that planet and star appear tightly separated in the sky. That geometry demands precise optics. Nearby systems may still offer targets where reflected light or thermal emission can be measured directly. Direct light would open a new set of possibilities. The planet could be observed without needing to cross the star. Spectra could be gathered from non-transiting worlds, while changes in brightness might reveal clouds, ice, oceans, or broad differences between day and night. No telescope would see cities, trees, or coastlines in ordinary detail. The first maps would be mathematical. As the planet moved through its orbit, the combined light from its visible hemisphere would change. A bright cloud deck could raise the reflected signal. A dark ocean could lower it. Ice near the night boundary might contribute a different spectral pattern. By comparing these changes with models, scientists could infer regions larger than continents. On a synchronously rotating planet, the map would have an unusual stability. The substellar region would remain under constant illumination. A persistent cloud shield might occupy the same broad area. The night side would contribute little reflected light, but could emit infrared warmth carried there by winds. Over many orbits, weather would move across a climate whose main geometry stayed fixed. That distinction may help separate lasting geography from passing clouds. A repeating dark region could indicate ocean or rock. A feature that changes from one orbit to the next might belong to weather. Variations linked to the star's activity could reveal haze formation, atmospheric loss, or chemical recovery after flares. Even then, ambiguity would remain. A bright surface may be ice, salt, cloud, or pale rock. A dark surface may be ocean, lava, mineral deposits, or biological pigments. Oxygen may come from life or from the loss of water. Methane may be produced by organisms, volcanism, or reactions between rock and water. The search for life will not be a search for one unmistakable color. It will be a search for a system that is difficult to explain without biology. That system would include the star's spectrum, the planet's mass and radius, its climate, surface pressure, atmospheric gases, orbital changes, and the chemical rates that should remove those gases over time. Evidence would grow through convergence. One observation might suggest liquid water, another a stable atmosphere, and a third gases held far from chemical balance. Years of monitoring might show that the pattern persists. At some point, a distant planet could become more than potentially habitable. It could become a place where the non-living explanations have been tested and found increasingly strained. Even such a result would be discussed carefully. The first credible sign of life beyond Earth may not feel like a sudden discovery. It may emerge through papers, reanalysis, disagreement, improved instruments, and repeated measurements until the remaining interpretation becomes difficult to ignore. The world itself would have been there throughout the debate. Its fixed star would continue to shine above the same hemisphere. Winds would cross the terminator. Clouds would gather over warm ground. Ice would remain beneath the dark sky. Any life present would continue its own chemistry, without knowing that a telescope far away had begun to notice. From Earth, the signal would be almost weightless. A few missing wavelengths, a small shift in heat, a pattern returning once each short year, and that faint pattern, the first outline of a climate that never sees noon. A climate that never sees noon asks us to separate habitability from familiarity. Earth has trained the human imagination to expect a moving sky. We understand warmth through sunrise, weather through seasons, and time through shadows that cross the ground. Even the word day carries two meanings here. It describes one rotation of the planet, and it describes the bright interval between morning and evening. On a locked world, those meanings come apart. One rotation is also one orbit. The planet turns, but the star remains fixed above the same region. There is no bright interval moving across the surface. Day is a place. Night is another place. Between them, time still passes. Radioactive elements decay, rock rises and erodes, molecules react. Organisms, if they exist, grow and divide. The absence of sunrise does not remove change. It only removes one of the most visible ways that change is measured. A civilization born on such a planet would build its first ideas of the cosmos from a different sky. On the day side, the star might remain visible through every lifetime. Its position would depend on location rather than hour. Near the substellar region, it would hang high, while closer to the terminator, it would rest near the horizon. Travel would change the sky more than waiting. A journey toward the light would raise the star. A journey toward the night would lower it. Direction and illumination would become closely linked. Maps might be organized by the angle of the star, the strength of the wind, or the distance from permanent darkness. The night side would offer another view entirely. Without direct starlight, the sky could become a natural observatory. Stars might remain visible whenever clouds allowed. The Milky Way could stretch overhead without sunrise erasing it. Planets in the same system might move against the background, their cycles providing some of the clearest clocks available. If the atmosphere carried heat well enough, settlements or ecosystems might persist far into that darkness. The sky above them would not rotate in exactly the way ours does, but it would still move because the planet is orbiting its star. Over one short year, distant stars would trace patterns, while the red dwarf remained hidden below the horizon. The inhabitants of such a world, if there ever are any, might discover the universe from the night before, understanding the star that warms the far side of their planet. Their earliest astronomy could begin with darkness as the ordinary condition of the sky. Their earliest geography could begin with light as a distant direction. This is speculation, but it grows from the physical structure of the planet. The same geometry that controls climate would also shape perception, travel, and measurement. Human beings have always turned repeated patterns into time. Long before mechanical clocks, people watched the sun, moon, stars, tides, and seasons. Those cycles became calendars and navigation systems. They linked one generation of observers to the next, notch, allowing knowledge to outlast the individual person who first noticed a pattern. A locked world would offer different cycles, but it would still offer repetition. Planets would return to familiar positions. Atmospheric waves might pass in regular intervals. The star could flare with patterns tied loosely to its rotation and magnetic activity. Moons, if stable moons were present, could cross the sky. Orbital seasons could shift the boundary of light. Time would still be written into the environment. It would simply be written in another alphabet. This matters because the search for life often begins with a hidden assumption that Earth provides the standard form of a living planet. Earth provides the only confirmed example, so the assumption is understandable. But an example is not the same as a rule. Liquid water does not require a 24-hour day. Atmospheric circulation does not require sunrise. Photosynthesis does not require the exact spectrum of the sun. Biological rhythms do not require a moving shadow. The laws of physics limit what worlds can do, but those limits leave room for many arrangements. A red dwarf planet may be one of them. Its greatest advantage may be duration. The smallest stars use their hydrogen so gradually that their stable lives may continue for trillions of years. Compared with them, the Sun belongs to a brief generation. It will spend roughly 10 billion years on the main sequence before changes in its core carry it into later stages. A low red dwarf may remain active as a hydrogen-burning star for hundreds or thousands of times longer. This creates a future that the present universe has never yet experienced. The cosmos is not old enough for any red dwarf to have completed its full main sequence life. Every one of these stars is still within the early portion of its possible existence. Even the first red dwarfs, formed after the birth of the earliest generations of stars, remain young compared with the lifetimes predicted for the smallest among them. Far in the future, stars like the Sun will be gone. Many larger stars will have ended as white dwarfs, neutron stars, or black holes. Star formation will decline as galaxies consume or lose the cold gas needed to create new suns. Red dwarfs will remain. Their light may become the dominant starlight of a much older universe. Around some of them, planets may continue orbiting through ages longer than the entire history that has passed so far. Whether those planets remain habitable is uncertain. Their interiors will cool. Geological activity may slow. Atmospheres may be altered by escape, impacts, or chemical exchange with the surface. Orbits can change through long gravitational interactions. Water may be lost, frozen, or buried. A long-lived star does not guarantee a long-lived biosphere. Still, duration creates possibilities that short-lived systems cannot offer. A planet that survives its star's active youth could enter an era of remarkable stability. The star's energy output would change very gradually. Climate could persist within a narrow range for spans that make Earth's history seem brief. Evolution, if it began, would have time to explore paths unavailable on a younger world. Complexity might arise. It might disappear. It might return in another form. There is no scientific reason to assume that more time always produces intelligence, or that intelligence follows a predictable direction. Evolution responds to local conditions. It has no required destination, but a trillion-year star provides an immense number of opportunities for change. It also changes the scale of failure. On Earth, a temporary loss of habitability could close a large fraction of the remaining time available before the Sun grows brighter. Around a red dwarf, the planet might pass through long frozen intervals, and later thaw through volcanic gases, orbital changes, or shifts in stellar behavior. A biosphere could be interrupted and still have more time ahead than the current age of the universe. These possibilities cannot yet be tested directly. They belong to models of stellar evolution, planetary climate, and deep time. But they follow from well-established differences in how small stars consume fuel. The red dwarf is not merely dim, it is patient on a scale the universe has barely begun to reveal. Somewhere tonight, a small star may be shining on the same hemisphere of a rocky planet that it illuminated billions of years ago. Winds may be crossing into the dark, ice may be moving beneath its own weight. Clouds may be gathering beneath the fixed point of light. Nothing there needs to resemble an earthly afternoon. The planet does not know that its key is strange to us. Its oceans, if they exist, respond only to gravity, temperature, chemistry, and motion. Its atmosphere follows pressure. Its rocks hold heat. Its molecules react according to the energy available. Familiarity has no place in those equations. From where you are now, beneath a sky shaped by Earth's rotation, the difference can feel immense. Yet the same physical laws connect both worlds. The light reaching a red dwarf planet is carried by the same kind of photons that cross your room. Gravity holds its atmosphere in the same way gravity holds the air above you. Heat moves from warmer places toward colder ones. Water freezes, melts, evaporates, and condenses according to pressure and temperature. The setting changes, the rules remain. This is why these planets matter even before one is found to be inhabited. They test how much variety those rules can produce. They ask whether a stable climate can exist beneath unmoving light, whether air can protect a world close to an active star, and whether life might find energy in a landscape divided between permanent day and permanent night. The answers will arrive slowly. One spectrum will limit an atmosphere. One phase curve will reveal moving heat. One nearby planet may show clouds. Another may show bare rock. Across years of observation, the category itself will become clearer. And perhaps one day, among the measurements, a world will appear whose atmosphere, temperature, and chemistry all point towards something active beneath the fixed red sun. Until then, the planets remain distant and unresolved. But they are no longer unimaginable. There is no single place on a tidally locked world where the story must end. It might end beneath the unmoving star, where clouds gather over warm oceans and reflect enough light to keep the surface below from overheating. It might end near the boundary of day and night, where winds cross a landscape of long shadows and carry moisture toward colder ground. It might end beneath ice on the dark hemisphere, where water remains liquid around heat rising from the planet's interior. Or it might not end at all. A world can continue changing for billions of years, while its star stays fixed in the sky. Mountains rise and erode, continents shift, volcanoes release gases, oceans absorb them, ice advances, retreats, and returns. A flare changes the upper atmosphere for a few hours, while deeper chemistry responds across centuries. The planet's rotation and orbit remain locked together, but almost everything within that pattern keeps moving. This is the central lesson offered by red dwarf planets. Tidal locking is not a frozen condition. It is a geometry. It tells us where the light falls. It does not by itself tell us the temperature of the ground, the thickness of the air, the depth of the oceans, or the fate of the atmosphere. Those depend on a history that begins during formation and continues through stellar activity, interior cooling, impacts, weathering, and escape. Two planets, receiving the same amount of starlight, therefore become very different places. One may lose its water early and remain bare. Another may keep a deep atmosphere that carries heat around the globe. A third may trap most of its water as ice, while preserving narrow seas beneath low clouds. A fourth may never have had enough water to begin with. The habitable zone is only the beginning of the question. It marks a range of possible energy. It does not certify a climate. For many years, the idea of a world with one permanent day and one permanent night seemed to place a hard limit on habitability. The bright side was imagined as scorched, the dark side as frozen, and the narrow band between them as the only possible refuge. The models now tell a more complicated story. Air can move heat. Oceans can move heat. Clouds can reflect light. Ice can store water. Rock and gas can exchange carbon. A planet with enough atmosphere may reduce the contrast between its hemispheres. A planet with little air may preserve that contrast almost completely. The range between those outcomes is wide, and it is governed by ordinary physics acting in an unfamiliar arrangement. That unfamiliarity is part of what makes these systems valuable. They force astronomy to test which features of Earth are necessary and which are merely local. A moving sun is local. A 24-hour rotation is local. A yellow-white star is local. A large moon is local. None of these can be assumed to be universal requirements for life. What may matter more are lasting conditions, stable liquid solvents, useful sources of energy, chemical ingredients, environmental gradients, and enough time for complex processes to develop. Red dwarf systems may provide some of these conditions in abundance and others only with difficulty. Their planets can be easier to detect, but difficult to interpret. Their stars can live for immense lifespans, but spend their youth releasing powerful radiation. Their habitable zones are close enough for frequent transits, but close enough for tides and stellar weather to dominate planetary evolution. Every advantage has a shadow. Every obstacle has exceptions. This is why future observations will not produce one answer for all red dwarf worlds. They will produce a catalogue of different outcomes. Some atmospheres will be missing. Some will be thin. Some may be dense and dry. Some may carry water vapor, clouds, or carbon dioxide in combinations that reveal active climates. A few may become the first rocky exoplanets, whose dayside and nightside temperatures are measured well enough to test global circulation directly. The first climate map of such a world may contain only a few broad regions, one warm area, one cooler area, a shifted bright zone where clouds or winds move heat away from the point beneath the star. It will not look like a map from Earth. There may be no coastlines, no mountain ranges, no visible storm systems. But it will be a beginning. For the first time, a distant rocky planet could become more than a radius, a mass, and an orbit. It could become a place with weather. From there, the questions deepen. Does the atmosphere remain stable through repeated flares? Does heat reach the night side? Do clouds gather near the fixed star? Is water present in the air or at the surface? Are the observed gases compatible with geology alone? Each answer will depend on careful measurement, and each measurement will be limited by the star, the instrument, and the distance between worlds. There will be false starts. Signals will disappear under better analysis. Atmospheric features will turn out to belong to stellar spots. Promising interpretations will narrow into less dramatic explanations. This is not failure. It is the method by which weak possibilities are removed and stronger ones remain. The planet does not become less interesting when one hypothesis is rejected. It becomes more clearly known, and knowing such a world clearly may require patience comparable, in a small, human way, to the patience of the star itself. Red dwarfs will continue shining long after the telescopes now observing them are gone. New instruments will replace old ones. Data gathered by one generation may be examined again by another. A planet considered unreachable in detail today may become a familiar target to astronomers who are not yet born. The same fixed light will still be falling on the same hemisphere. On that distant surface, there may be no sunrise, there may be no noon crossing overhead, there may be no evening, but there may be winds, there may be rain, there may be ice moving under pressure, there may be chemistry repeating in warm water, there may be life, or there may be only the long interaction of air, rock, ocean, and light. For now, the honest position is not certainty, it is attention. These planets deserve it because they are common, nearby, and physically different from the only inhabited world we know. They occupy a region where astronomy can move from detection toward climate, and perhaps one day from climate toward biology. They also remind us that the universe does not arrange every living possibility around the habits of Earth. A world can be divided between permanent light and permanent dark, and still remain connected by motion. The star can stay in one place, while the planet continues to change beneath it. The wind keeps crossing the night,